And then I would like to invite a first speaker, who is Jeroen van der Brand, who works for TNO Holst Center at the high-tech campus in Eindhoven. And Jeroen will provide a presentation on printed and sustainable electronics and the challenges ahead.
Thank you very much. So first of all, it's a pleasure to be here after so many years. I think the last time was 4 years ago with all the COVID happenings, but I'm very glad to be here. So indeed, my name is Jeroen van der Brand. I'm a department head at Holst Center in Eindhoven. I will explain what Holst Center is. And in this presentation, I will talk to you about printed electronics, but then in particular, actually the new topics that we are working on at Holst Center. So first, maybe a short introduction to Holst Center for those of you who are not familiar with it yet. So Holst Center is an independent, non-for-profit R&D institute founded in 2005, so already quite some years ago. There are two organizations behind this, TNO and IMEC. And TNO is in the Netherlands a bit like Fraunhofer is in Germany. It's the central Dutch research organization. And IMEC, I think you all know, it's the famous Belgium Semiconductor Institute. So in Holst Center, we have around 260 own employees, and they're actually all located in the Holst Center premises, of which you see a photograph on this slide. So if you would try to summarize on one slide what we do in this Holst Center, it's a development of key enabling technologies and building blocks for actually two sort of domains. One is wireless low-power electronics, which is the IMEC part of Holst Center, and the TNO part of Holst Center focuses on free-form electronics. So we do a lot on printed, 3D, etc. So if you look at the kind of applications that we focus on, we try to find it really at the cross point between wireless low-power and free-form. So we do quite a lot on medical devices. So in my presentation of today, I will focus exclusively on the printed electronics activities at Holst Center. Now, as you may be aware, the way that PCBs are today is actually they are rigid, they are thick, and they are bulky, and there are quite some applications upcoming where you cannot use these rigid PCBs anymore. For example, wearables, you don't want a rigid PCB on your body. Now, secondly, as you may also be aware, PCB manufacturing, and it was already touched upon in the introduction, uses quite environmentally unfriendly materials and processes. So what we do at Holst Center is actually to develop the enabling printed electronic technologies for a next generation of printed circuit boards that can be flexible, stretchable, or three-dimensional. Now, the benefits of that are actually at the bottom of the slide. It allows an easier final product integration, so the PCB becomes the product. It gives increased design freedom. It gives a better fit for function, a lower environmental impact, as I will explain in more detail later on. And it also gives better volume scalability. So it's easy to do small series, but also very large volumes. So actually, at Holst Center, we have quite a long track record in printed electronics, and we have been helping and advancing the industry on printed electronics already since 2007. So we have been helping end-user companies with using printed electronics for their applications. And actually, at the bottom of the slide, you see some examples of devices that we helped realize. There are also quite some Japanese companies examples in there. So in the medical field, we have been doing quite a lot of patches, but also smart baby beds. In automotive, we are and have been doing human-machine interfaces, but also tire sensors. And in consumer electronics, we have been doing stretchable displays, but also a smart golf shirt, as you can see at the top sort of left. Now, next to this, we are also helping material companies with developing new materials for new domains, like stretchable inks, dry electrode materials, these kind of things. And we have been helping quite a lot of equipment companies with all kind of new technologies. Now, next to helping industry, we also create our own startups. And in the field of printed electronics, actually since 2019, we have been launching 5 startups. 2 of them will also present later today. So in 2019, we founded JEROEN, who are developing a tool for lift printing of interconnect materials. In 2021, we have been launching Traxon. They will speak also later today. That's a foundry for printed electronics. In 2022, we have been launching Phonontech, who are developing a tool for a quite disruptive thermal printing technology. And recently, we actually added 2 startups to it, TouchWaves and IconHealth. TouchWaves is developing smart clothing for breathing guidance, and IconHealth a medical patch for cardiac care. So with this, I want to sort of give the message that printed electronics has matured since 2007, and currently it is being used by the industry. So the technologies and the materials are mature and reliable, and also partially also owing to Traxon, the upscaling is really beginning to take shape. But we are an R&D institute, so what does it mean for us? We also see that actually there are new topics upcoming where we as an R&D institute can do all kinds of new developments. I will touch upon 2 of these topics today. One is on sustainable electronics, where printed electronics is really being recognized as a key contributor to reducing the environmental impact of electronics. And the second one is 3D printed electronics, where printed electronics is seen as a way to create products that you cannot create in any other way. So I will discuss these topics one by one, starting with sustainable electronics. It was already mentioned in the introduction, so every year 57 million tons of e-waste are being produced, and this is actually enough to cover land the size of Manhattan. So it's really a lot of waste that's being created. Now, out of these 57 million tons, actually less than 20% is being properly recycled, and the rest is dumped, traded, or recycled under inferior conditions. Now, as you can imagine, this contributes to all kinds of environmental problems like energy crisis, global warming, material scarcity, etc. Now, in particular in Europe, there are very strong driving forces to do something about this. So in the EU, there's actually a lot of legislation upcoming, like European Green Deal, Digital Product Passport, and Eco-Design Directive. But in Europe, there's also a lot of pressure from society to really make electronics more sustainable than it is now. Now, we believe, and I will actually prove this a little bit later on, is that printed electronics can really help in making electronics more sustainable. So from a product design perspective, printed electronics allows weight and space reduction because product and electronics become one. They really become tightly integrated, and sometimes even the PCB can be fully removed. Now, from a production perspective, printed electronics actually results in less material consumption. It uses less environmentally unfriendly materials, and it also allows to use recycled or bio-based materials. So to prove this a little bit, I have 2 examples of analysis that were performed on this. So the first one is from the Finnish company Taktotech. It's a scale-up in Finland, in Europe. And they are actually developing a technology called in-mold structural electronics. And the principle on this is that a printed electronics film is used as an inlay in an injection molded part. Now, they actually analyzed a specific automotive part, which you can see on the top left. And when made with conventional technologies, 64 parts and a PCB were needed, which, as you can imagine, is quite difficult to assemble. The final part had a thickness of 45 millimeters and weighed 650 grams. Now, the same part made with this Taktotech, this in-mold structural electronics technology, was a single molded part with a small PCB. The final part was only 3 millimeters thick and weighed 150 grams. Now, from their analysis, and you can see the data here on the right-hand side, they concluded that 33% savings in global warming potential, which is sort of metric for environmental impact, could be achieved by combining more environmentally friendly manufacturing and reduction of usage of materials. So that's quite impressive, I think. So second proof point of this is an analysis performed at the University of Amsterdam in the Netherlands. They actually compared production of a conventional PCB versus a printed electronics PCB. So here they assumed 2 circuit layers, dimensions of 10 by 10 centimeter, 40% metal coverage and a volume of 25,000 pieces. Now the data are shown at the bottom of this slide, and as you can see, printed electronics really results in a significant reduction of materials and also less energy consumption and also lower CO2 emissions. So we have started to work on sustainable electronics, I think 3-4 years ago, and here we really want to do innovations across the full product life cycle, which you can see here on this slide. So from a production perspective, we aim to further reduce the environmental impact of printed electronics with topics like printed copper and using recycled materials. For the use phase, we want to improve the reliability of printed electronics so it can be used for more applications and it can be used for longer periods of time. For the end of life, we work on technologies for separation after usage. And for the design phase, we have sort of starting activities on LCA analysis, design for recycling, these kind of things. So I will discuss 2 topics, but only a little bit shortly. The first one is printed copper. I will talk about that, and technologies for separation after the end of life. So starting with the first one. Now, if you're a bit familiar with printed electronics, you know actually that almost exclusively silver inks are being used to create the electronic circuits. However, silver has a very high global warming potential. It's very bad for the environment. And as you also may be aware, it's quite an expensive material. So a good alternative to silver is actually copper. So copper has a much lower global warming potential. It's a factor 90 lower if you compare the numbers. And fortunately, it's even cheaper than silver. So what's another advantage at the moment is that there are really a lot of new copper inks being developed by various suppliers. So Print PCB, Copprint, Cuprion, they are all making new copper-based inks. So we recently did a quite extensive benchmarking study of state-of-the-art copper inks. I will show some results of that, first printing results. So on the top left, you see a reference silver material, DuPont 5025, which is sort of the benchmark in this field. And the other 3 are from the best copper inks that we could find. And if you look at these printing results, you can see that in particular number 2 and number 3 show results that come quite close to silver already. So that's very impressive. So we did a further analysis of these materials, and some of the results are summarized in this table. So we looked at resistivity, we looked at adhesion, and we looked at feature resolution. Now, if you look at the data, you can actually see that current state-of-the-art copper inks come quite close, and in case of number 2, even surpass state-of-the-art silver inks. Now, it's good to mention that these materials are still under development, so we do expect still some further improvements. And I think it's good to mention that this is still a topic where other material companies can also play a role if interested. It's really a hot topic at the moment. So to prove a little bit the maturity of the technology, we also created the demonstrator. You can see it on this slide. So here we printed copper tracks and we soldered LEDs on it. And if you can see, it works quite well already. So this concludes what I wanted to say about printed copper. Now, the second topic is separation after end of life. So I told to you actually that printed electronics allows for products where the electronics is embedded inside the product. So it's not a separate part anymore. But then what about the end of life? How do you get them apart again? So here we are developing actually a new technology to separate printed electronics from products, and I will...
TNO at Holst Center is aware of its responsibility to reduce future e-waste. We continue to innovate and find clever solutions to make electronics truly sustainable. Electronics embedded in plastic are all around us. In the devices you work with, the home you live in, the car that you drive. We provide hybrid printed electronics with great design freedom and complex functionality in an extremely durable package. But they're certainly not perfect. When these components break, they're impossible to repair or recycle. This means they either end up in landfills abroad, or they are shredded or incinerated, polluting the environment and wasting precious materials. We must do better. We are dedicated to creating hybrid printed electronics that are fully circular. How? By developing an advanced eco-design with a revolutionary dismantling process. Let's take a closer look at this component embedded in plastic. It consists of several inseparable layers, including the plastic substrate with the printed circuitry. It contains silver, a scarce and expensive metal. SMD components such as sensors, resistors, LEDs, and microchips. Plus a thermoplastic encapsulation that accounts for most of the component's weight. Our scientists have come up with an elegant yet effective dismantling solution. By adding a temporary bonding layer right between the circuitry and encapsulation, we can easily, cleanly, and safely remove the bulk of the plastic at end of life. Without compromising on durability, we're able to recycle all plastic and metal components and reuse the scarce silver from the circuitry. Our technology even paves the way for repairing hybrid printed electronics, which could dramatically improve their lifespan. Stay in the lead with our sustainable electronic solutions. Contact TNO at Holst Center today to discuss the possibilities.
So what this movie actually showed is that we have actually created a unique separation approach, a dismantling approach, to cleanly separate printed electronics from products. And we do this by adding an extra layer on top of the circuit that actually helps in this separation. And this separation is triggerable either by light or heat, where we have both options available. So I will now show an example device build-up where we use this technology, which is an in-mold electronics lighting device. So here we start from a polycarbonate substrate. You can see it on the right-hand side. On top of this, we print graphics, we print electronics, and we assemble the components. And then on top of everything, we print this special separation layer. That's actually the blue layer that you see. And then we overmold everything using injection molding. Now the final device is actually shown here in this photograph. Now as you can see, this separation layer actually has no influence on the functionality or the operations. So then as a next step, we put these samples through reliability testing. On the left-hand side, you see the reference device where there's no separation layer. And on the right-hand side is a device with included separation layer. And as you can see from these pictures, both of these devices actually could withstand 1,000 hours at 85. So reliability is quite good. Now after all of this, we then separated the device again into the individual layers. And as you can see from this photograph, this actually results in quite clean layers, which are then ready for recycling or repair. So this concludes what I wanted to say about sustainable, maybe what's next for us. So going forward, we actually have two main application areas that we focus on. So the first one is in-mold electronics. That's the technology that I talked about. And here we aim for fully circular manufacturing. And the driver here is that in particular in Europe, automotive is really strongly pushing to make it more sustainable. The second domain is medical patches, and here we aim to make them fully biodegradable. And here the driver is, as you can imagine, this is a really large volume application with a lot of potential e-waste. So I think we have a responsibility there to make them biodegradable. So what does it mean from a technology perspective? So we continue with reducing the impact of printed electronics, the environmental impact. So we are looking at recycled and bio-based materials. And we will also continue development of technologies for the end of life, where, for example, we are working on all kind of reversible adhesives also. So this brings me to the second new topic at Holst Center, which is 3D printed electronics, and I will again show first the movie about this.
An in-ear device. So many electronics integrated in such a small space. In the future, any electronic product can be custom-made. Customers demand new models to be marketed rapidly. It is essential to keep up with this demand while reducing the environmental impact. 3D printed electronics is a fast and digital manufacturing method enabling free-form electronic products. Have a look at the latest research from Holst Center. The process starts by coating a uniform layer of structural material. The specialized tool allows fully controlled and fast coating. With a high-resolution light engine, the material is selectively cured. Due to parallel processing, large areas can be cured at high throughputs. The uncured material is removed in a cleaning step. Highly precise cavities are left for circuitry, vertical interconnects, and placing electronic components. All components are automatically placed with high accuracy in all dimensions. Subsequently, additional layers are printed to form grooves for the conductive tracks and interconnections. They are made by filling the empty grooves and cavities with conductive pastes. Afterwards, the paste is cured to form a highly conductive electronic circuit. Reliable, high-resolution connections are realized using this method. The building process is then repeated to finish the product. This fast and digital manufacturing method enables free-form electronic products that cannot be achieved using the current production methods. Custom-made products become possible for consumer electronics, automotive, and other industries. Contact us to find out how we can help you.
So as the movie showed a little bit, 3D printed electronics is actually a fully new way of making electronic products where the progress in 3D printing is combined with the progress in printed electronics. Now, as you can imagine, this brings quite some advantages across various fields. There's a summary here on this slide. I think the most important one is it reduces the number of parts. It makes it easier to assemble things, but it also allows much easier small volume manufacturing and maybe even make on demand. So also here we have been working already for a couple of years on this technology, and actually our ambition is to progress beyond state of the art in this field, where we want to improve on resolution. Our target is here 10 micrometer line and spacing, and we want to improve on material flexibility. Now the process was already shown in the movie, but I will repeat it here. It's actually at the bottom, these pictures that you see. And so we start with printing cavities for the components. We use standard SLA technology for it, which is a common 3D printing technology. Then we place the components in the cavities. We print in the next layer the groove for the circuit. We fill this with a conductive ink. We cure this ink, and then we repeat it again to fully complete the product. Now, this is a completely new technology, and the tools for doing that actually didn't exist yet, so we had to build it ourselves. And what you see on this photograph on the left-hand side is the machine that we built around this technology. And on the right-hand side, you can see what it looks like on the inside. Now, the current status here is that we can do the full process flow that was shown in the movie, but it's not yet fully optimized. So here the tool is still under development. So I will show two examples of devices that we actually created here. And the first one is from semiconductor chip packaging, which is work that we do together with CITC. Francesca will present about that later. So here we had to do stressless chip packaging of a silicon-based sensor that should not deform upon temperature changes. So what we created here is an all-printed structure, which you can see in cross-section actually in this figure. And in this printed structure, the sensor is mounted floating and mechanically decoupled from the rest of the package structure. Now, we were successful in doing that You can see a photograph of the final device that we printed, but up to now we did use only a dummy silicon die, so that's still work in progress. So the second example that I would like to show to you is from the medical field, and that's work that we do together with Philips, a medical company in the Netherlands. That's about a lead extractor. Now, as you may be aware, heart pacemakers don't last a lifetime, and after roughly 10 to 15 years, the leads need to be replaced, and this is actually done by a so-called lead extractor. Now, the surgical procedure for this is currently performed by touch, so it requires a very experienced surgeon to do that. And there's always the risk of scar tissue being formed on the heart, and of course you would like to prevent that. Now, to improve upon this, highly localized ultrasound imaging at the tip of the lead extractor is actually a very attractive proposition. So Philips actually asked us if using 3D printed electronics, we could integrate ultrasound at the tip of the extractor because they had no other technology to do that. Now, this is very much work in progress. So we are at the moment still working on the individual building blocks, but maybe to show you what needs to be created here, it's shown schematically on the left-hand side. It's actually a 6 millimeter diameter 3D printed element, and in this element there are embedded chips, embedded wiring, and CMUT ultrasound transducers. And after printing, this device, as you can see on the right-hand side, is to be then attached to the lead extractor for performing the procedure. So as mentioned already, this is work in progress, so I will just show you some building blocks. It's not completely done yet. And so one of the building blocks that you see here on this slide, on the left-hand side, is actually there we successfully embedded CMUT drivers, CMUT ultrasound transducer inside a 3D printed structure, and you can see the individual steps. And to give you some idea of size, here it's shown actually next to a coin, so it's extremely small structure. So another building block is shown on this slide, and this is actually where we electrically interconnected a CMUT driver. Here the bond pads are 90 micrometers small, and as you can see also there we could do that successfully. So this almost brings me to the end of my presentation and the part on 3D printed electronics. So what's next here? So we are very much maturing the technology, and we are maturing the tooling of it. There's still a lot of work to be done, but we are already exploring some applications, as you've seen. So we see a lot of interest from defense industry and space, actually, to have very lightweight, fully integrated sensors. And we see an interest from semicon field, actually, to create packages that are not possible with other technologies. And I think maybe as a final comment, also here, just like sustainable electronics, there's really a need for material companies here to develop all kind of improved materials. And that concludes my presentation. Thank you very much.
I think it's very interesting, Jeroen, to hear about the projects you're working on right now at Holst Center. I was wondering, when you look at sustainable electronics, and you look at like in 10 years from now, where do you think we stand in 10 years from now?
I can mostly speak for Europe, but so if you look at the pressure that's currently being put on everyone in Europe, then I think we have to make, and we will make, big steps. For us, for printed electronics, it's a very big opportunity. So I hope we can play a role in that, but certainly there will be a lot of progress made. It has to. Yeah.
Good to hear that. Yeah.
Thank you.
Thanks a lot.
Thank you.